This is question number 1 on our limits quiz. And what we have here is a basic limit to infinity. So we have the limit as n approaches infinity of 3n cubed minus 5n all over n cubed minus 2n squared plus 1. Remember, for a limit as our variable approaches infinity, what we want to do is find the highest power. We have the highest power in the numerator here and the highest power in the denominator here. They are the same. So because we know that both of those limits are the same, both of those powers are the same, we're going to take the leading coefficient, which are 3 and 1, and simply put them in a ratio, and we get 3 over 1, which is 3, choice D. This is question number 2 from our limits quiz, and this is a limit to a number. So the first thing we're going to do here is we're going to just fill in the 0 and see if we can get an answer. So the limit as theta approaches 0 of 1 minus cosine of theta over 2 sine squared of theta. So let's go ahead and fill this in. And what we're going to get is 1 minus cosine of 0 over 2 sine squared of 0. And cosine of 0 is, of course, 1. And the sine of 0 is 0, so this is going to be 0 squared, meaning 0. So we've got 0 over 0, which is an indeterminate form. So what do we do? Well, let's try to factor this and simplify it somehow. And let's recall some of our trigonometric identities. You will notice here that we have sine squared of theta. And we should recall that sine squared of theta plus cosine squared of theta is equal to 1. So then we can reduce this out and say that the sine squared of theta is 1 minus the cosine squared of theta. Now, why did I do that? Well, if we have the numerator as 1 minus cosine of theta, getting it all into one trig ratio could be very helpful to simplifying the problem. So we've got 1 minus cosine of theta over 2 times 1 minus cosine squared of theta. Now, let's factor 1 minus cosine squared of theta using difference of squares. So if we had, for instance, 1 minus x squared, we could factor that into 1 minus x times 1 plus x. So here then, this would factor into 1 minus cosine of theta times 1 plus cosine of theta. So we're going to replace the 1 minus cosine squared of theta with 2 times 1 minus cos of theta, 1 plus cos of theta. And now you can see that we could divide out the 1 minus cosine of theta and be left with a 1 up top. So now we've got the simplified version here, and we're going to take the limit as theta approaches 0 of 1 over 2 times 1 plus cosine of theta. So then we fill in a 0 here, and we're going to get the cosine of 0 to be 1. Now we've got 1 over 2 times 2, which is 1/4. So check the number first. We get an indeterminate form, then use all the tools in our trigonometry toolbox to simplify the problem and get our answer. This is question number 3 on our Chapter 1 limits quiz. And what we have here is a special limit. And it may not be immediately obvious that it's a special limit, but our first step in dealing with cosecant is changing that to 1 over sine. So we've got the limit as x approaches 0 of x times 1 over the sine of x. Now, we may not know right away what the cosecant of 0 is, and that's why we change it to a sine. But we should know that the sine of 0 is 0. So this simplifies to the limit as x approaches 0 of x over sine of x. Now, if we actually just put in the 0 here, as we normally would, we're going to get 0 over the sine of 0, which is 0 over 0 and is thus indeterminate. And we need to remember that the limit as x approaches 0 of sine of x over x is 1. Well, all this is the reciprocal of that. So the reciprocal of 1 is also 1, and then we know that the limit as x approaches 0 of x over sine of x is also 1, or 1 over 1, again, reciprocating the 1 just yields 1 again. So the answer is choice D. This is question 4 on our limits chapter quiz. And what we have here is a simple limit to infinity. We've got the limit as n approaches infinity of 4n squared over n squared plus 10,000n. All we have to remember here is that the highest powers are all that matter. And we have equivalent highest powers. We have a squared in the top and in the bottom. So all we have to do is take the leading coefficients of the highest powers, which are 4 and de facto 1. This 10,000n is completely irrelevant because it's a lower power and thus won't increase as fast as we approach infinity. So all this is just 4 over 1, which is just 4, or choice D. This is question number 5 on our chapter 1 limits quiz. And here we have a limit as x approaches a. So here we have if a is not equal to 0, then the limit as x approaches a of x squared minus a squared over x to the 4th minus a to the 4th is what? So a is a number. It's a constant in this case. So let's actually fill in a for x. And what we're going to get here is we're going to get a squared minus a squared and a to the 4th minus a to the 4th, which is 0 over 0. So we have our indeterminate. When we have an indeterminate form, what we should be doing is trying to factor it out and trying to remove that removable discontinuity. So if we factor the top here, we'll go back to x squared minus a squared and x to the 4th minus a to the 4th, the limit as x approaches a. If we factor the top, we're going to get x minus a, x plus a. And if we factor the bottom here, we're going to get x squared minus a squared, x squared plus a squared. These are both differences of perfect squares. And we can then take the x squared minus a squared a step further and get x minus a, x plus a up top, x minus a, x plus a, x squared plus a squared. We can divide out both of these and be left with 1 over x squared plus a squared. Now we don't have that discontinuity anymore, so all we have to do is fill in a for x, and we're going to get 1 over a squared plus a squared, or 1 over 2a squared. So the process is the same if we were approaching any number. So all we have to do here is fill in a, recognize that we have an indeterminate form, and anytime we have an indeterminate form, we should be looking to factor and divide out that removable discontinuity that causes that 0 over 0 form. So the answer then is choice B. This is question number 6 on our limits chapter 1 quiz. Now we have here is a limit to a number. The limit as x approaches 1 of x over ln of x. Now what we want to do is fill in 1, as we normally would. And what we're going to get here is 1 over 0. The ln of 1 is 0, because it's basically the log base e of 1. So it's asking us e to what power is 1, and that is going to be the 0th power, which means that this is 0. Now, what that means is this is not an indeterminate form. This is either a positive or a negative infinity, or does not exist. So at this point, we can arrive quite comfortably at the fact that this answer has to be E, because the other answer choices don't feature a positive or a negative infinity. But let's also take a look at the graph here. And we'll see here that we have our 1, we have the asymptote. And we see that the left side is going down toward negative infinity and the right side is going up toward positive infinity. So the left-hand limit is negative infinity, the right-hand limit is positive infinity, which means that our limit does not exist. So the answer is E. We can use process of elimination, or we can use a graph here. This is question number 7 on our Chapter 1 Limits quiz. And we have somewhat of a more difficult question here with a little bit more arbitrary concepts, because this isn't a polynomial question, this isn't a rational expression of polynomial functions. It's a rational expression that involves a power function and an exponential function. So we have here is we have x to the k, where k is some positive integer, and we have e to the x in the denominator. And the question is, what happens as x approaches infinity? Well, so the top function here is a standard polynomial function. It's a monomial because it's only one term, but it's a polynomial function in the sense that it's x, the variable, to some constant power. And then the denominator here is our exponential function because the x is actually in the exponent. So which one increases at a faster rate? Well, let's take a look at the calculator, and I'm just going to use 2 here for for k. So if we just graph this, we'll see that we have kind of a line that seems to be getting closer to the x-axis, which would lead us to believe that the limit here is going to be 0. Let's take a look at the table, and we'll definitively be able to see that we're getting smaller and smaller and closer to 0. Now, notice we do actually get into some scientific notation here. This is 8.8 times 10 to the negative 4th, which is a really, really small number. And then we continue x times 10 to the negative 7th, and so on and so forth. So our scientific notation even leads us to believe that this is going to get closer to 0. And the answer here is going to be choice A. Now, as a good general rule, a to the x, where x is the exponent, tends to get larger faster, or tends to increase in value faster than does x to the a, where the x is in the base. This is question number 8 on our Chapter 1 Limits quiz, and this is kind of a graphical question. So the graph of the function f is shown in the figure above. Which of the following statements about f is true? So we've got a, and we've got b. Those are our two x values. So we have to go through these one answer choice at a time. The first is asking the limit as x approaches a of f of x is equal to the limit as x approaches b of f of x. Well, let's take a look. So the limit as x approaches a of f of x is 2. The limit as x approaches b of f of x actually is going to not exist because we have a left-hand limit that is 2 and a right-hand limit that is 1. So choice A is not true. We're looking for the one that is true. If we look, though, choice B actually tells us something that we already know. We know the limit as x approaches a is, in fact, 2, so we know that that's the answer. Let's just go over the other 3 to be certain. The limit as x approaches b is not 2. It does not exist. The left-hand limit is 2, but the right-hand limit is 1. Same thing with D. This is a D and E. But the limit as x approaches a of f of x definitely exists because both the left and the right-hand limit are the same. This is question number 9 on our Chapter 1 Limits Review quiz. And what we have here is a definition question. So we are told that the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h is equal to 5. And you should recognize this as the f of x plus h minus f of x all over h, which is the definition of the derivative. So since we know that this is equal to 5, when x is equal to 2, we know that the derivative is 5. So that means that the function is differentiable. We also know that if a function is differentiable, then it must be continuous at that point. The converse isn't necessarily true. Not all continuous functions are differentiable, but all differentiable functions are in fact continuous at that point. So that means choice 1 is also true. Based on the answer choices alone, we don't have a choice for 1, 2, and 3. And we know 1 and 2 to be true, so the answer has to be choice C. Now, we do have a possible condition with respect to answer choice 3 that we need to investigate. This is saying that the derivative of f is continuous at x is equal to 2. The problem is we don't actually know the derivative function. So, because we don't know the derivative function, we have no way of knowing whether the derivative function is continuous at that point, or whether it merely exists. So just because a function is differentiable doesn't mean that the derivative has to be continuous at that point. It does mean that f of x is continuous at that point. But it does not necessarily mean that f prime of x has to be continuous as well. So the answer is choice C. We don't know whether 3 is true, but we certainly know that 1 and 2 must be true in that scenario. This is question number 9 on our Chapter 1 Limits Review quiz. And what we have here is a definition question. So we are told that the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h is equal to 5. And you should recognize this as the f of x plus h minus f of x all over h, which is the definition of the derivative. So since we know that this is equal to 5, when x is equal to 2, we know that the derivative is 5. So that means that the function is differentiable. We also know that if a function is differentiable, then it must be continuous at that point. The converse isn't necessarily true. Not all continuous functions are differentiable, but all differentiable functions are in fact continuous at that point. So that means choice 1 is also true. Based on the answer choices alone, we don't have a choice for 1, 2, and 3. And we know 1 and 2 to be true, so the answer has to be choice C. Now, we do have a possible condition with respect to answer choice 3 that we need to investigate. This is saying that the derivative of f is continuous at x is equal to 2. The problem is we don't actually know the derivative function. So because we don't know the derivative function, we have no way of knowing whether the derivative function is continuous at that point, or whether it merely exists. So just because a function is differentiable doesn't mean that the derivative has to be continuous at that point. It does mean that f of x is continuous at that point. But it does not necessarily mean that f prime of x has to be continuous as well. So the answer is choice C. We don't know whether 3 is true, but we certainly know that 1 and 2 must be true in that scenario. This is question number 10 on our Chapter 1 Limits Review quiz. And what we have here is a definition question. So we have the limit as x approaches 3 of f of x is equal to 7. And the question is, which of the following must be true? And this is really important because all of these things may be true, but it doesn't actually mean that they must be true. The answer here is actually going to be choice A. Let me explain why none of 1, 2, or 3 must be true. So for 1, we could have a case where we have a limit like this. The limit still exists, but we may have a hole. So the hole would prevent choice 1 from being true. And for that same reason, just because there's a limit, again, there may be a hole, which means that if it's not continuous, it's not going to be differentiable at that point either. And finally, choice number 3 just because there's a limit doesn't mean that we have an actual value here. So the limit doesn't have to equal the function value. If it does, then we know it's also continuous. So the answer here is none of the above, because we actually have, the limit tells us nothing about the other properties. This is question number 11 on our Limits Chapter 1 review quiz. And what we have here is a definition question about continuity and differentiability. So let's start by figuring out whether the function is defined and whether it's continuous. Those are relatively easy. At x equals 3, the function given by this piecewise defined function, well, it's definitely going to be defined because we do include 3 here. So we can take the f of 3 by using the domain that includes the 3. And that's going to be 6 times 3 minus 9, which is just 9. So the function is definitely defined. And we can pretty easily figure out if it's going to be continuous by checking the left-hand and right-hand limits as x approaches 3. For the left-hand limit, we're going to use the part of the domain that's the left side, so less than 3, so it's going to be 3 squared, which is 9. And the right-hand limit we actually already did inadvertently here, because the right-hand limit is going to include the part of the function that is defined to the right of the 3. So it's going to be 6 times 3 minus 9, which is 9. Since the left and the right-hand limits are equal and equal to the function, we know that the function is continuous. So it's not going to be choice C, and it's not going to be choice D. Now, in order to determine whether this is differentiable, we have to do quite a bit of work. So here, we need to take the derivative of both portions of this function. Now, why do we have to take both? We have to take both because we need to see that the derivative from the left side is going to be the same as the derivative from the right side. Otherwise, we're not actually going to have a derivative at that point. So the f prime of x here, we need to make sure that the slope from the left portion of the function matches the slope from the right portion of the function, or we actually have a sharp point. So here, we have to take the derivative here, and we will use the limit as h approaches 0 of f of x plus h minus f of x all over h. So let's do that, and we'll use the top function first, the x squared. So x plus h for the top function, the f of x plus h, is x plus h all squared, which is x squared plus 2xh plus h squared by virtue of FOIL. The f of x is just x squared. So we will take the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared all over h. And you'll see that the x squared subtract out neatly. And then we can divide everything by h. We've done this a few times already. Now we can take the limit as h approaches 0 of 2x plus h, and we're going to get 2x, and we're using 3 here. So the f prime of 3 from the left side is going to be 6. We should verify then that the right-hand portion of the derivative is also the same. So the f prime of x for the bottom function here, the f of x plus h is going to be 6x plus h minus 9. So we've got 6x plus 6h minus 9, having distributed the 6. The f of x is just 6x minus 9, so we're going to do minus 6x minus 9 all over h. The 6x's subtract out, as do the 9's, because this is minus a negative 9, and we are left with just 6h over h, which is now just 6. So the f prime of x for the bottom function here is 6 at all points, so the f prime of 3 here is also 6. The reason it's important to test both parts, even though this does not include the 3, is if we have a function that looks something like this. We know this is a parabola, and then we know that this is a straight line, the 6x minus 9. Let's say that their slopes were like so. We would be able to calculate the derivative from the right side to be whatever it is. But the left side derivative, we'd get a sharp point. We would have two differing slopes depending on which one we measured. Because we got the same value, we can actually conclude that the slope of the derivative function at this point is exactly the same as the slope of the linear function that continues thereafter, and therefore we are able to get one derivative, meaning this function is both continuous and differentiable. If all else fails, we can graph this on the graphing calculator and just see if it creates a straight line at that point. Not a bad way to go about it either, but this is a little bit more complete. Also, in the next chapter, you're going to learn how to do the derivative for functions like this much faster and much more efficiently, so then this problem becomes much less of an imposition. This is question number 12 on our Chapter 1 Limits Review quiz. It's the final question on this quiz. Let's take a look. So what we have here is a function that is piecewise defined, and I want the limit as x approaches 2. Now notice that 2 is where our function changes, so what we have to do is take the left-hand limit using this part of the domain, and then the right-hand limit using this part of the domain. So the limit as x approaches 2 from the left would be the limit of ln of x. So we're going to get ln of 2 because this is the left-hand limit. These are values of x that are left of 2. And then the limit as x approaches 2 from the right would be of x squared ln of x. So we're going to get 2 squared ln of 2, which is 4 ln of 2. Because the left-hand limit and the right-hand limit are unequal, we know that the limit as x approaches 2 of this function, this piecewise defined function, does not exist. And the answer is choice E.